So a lot of you asked about problem 9 also, which I thought was kind of a fun problem. I didn't expect a little twist in it towards the end. So anyway, we have this nice looking function, and x is defined as less than or equal to a. We don't know much about a. And here's a nice graph. So first question, find the largest value of a such that f has an inverse function. Well, something's going to have an inverse that is a function if it passes the horizontal line test. Because when you do an inverse, it switches horizontal to vertical, and a function can't be intersected twice by a vertical line. So what I'm noticing is that this function is decreasing until this point here. And so this point right here is our a value. And so right here, we can label it as a and f of a. So we're going to try to determine that point. Luckily, it's a minimum, and so we can use some derivatives to find the minimum value there. Okay, so that's what we're trying to do. So let's scroll back up to be able to see our function here. And so I'm going to take the derivative and set it equal to 0. So f prime of x, when you have e to the x, it stays the same. Then you do the chain rule. So derivative of 2x is 2. 6e to the x stays the same. The derivative of 5 is nothing. We're trying to find a minimum, so we're setting that equal to 0. Then you can factor out from both of those terms. They're both even, and they both have an e to the x. The first term would be multiplied by another e to the x. The second term would be multiplied by a 3. So now we factored it. Now we can use the zero product property. So is it possible for 2e to the x to equal 0? No, that never reaches 0. Is it possible for e to the x minus 3 to equal 0? Yes. If e to the x is equal to 3, take the natural log of both sides, natural log of 3. So now we know that when x is the natural log of 3, there's going to be a derivative of 0. Because we have the graph, we can assume that this is this point right here. And that also matches up visually with what the natural log of 3 is, because the natural log of 3 is just going to be a hair bigger than 1. So you could move on here because you have the graph. Or if you wanted to just really be certain, you can use the second derivative test. And if you take the second derivative, you'll see it's 4e to the 2x, because we did the chain rule again, minus 6e to the x. And so then if you substituted f double prime of the natural log of 3, you have 4e to the 2 natural log of 3 minus 6e to the natural log of 3. And what's really nice is, of course, you're working with e here. And so e and natural log cancel out. And so you really have 4 times 9, because it was 2 natural log of 3. So you square the value, and 6 times 3. And this is positive. Now, why does that matter? When the second derivative is positive, it's concave up. And so now we've proved that that's the minimum value. I would say that this part right here is a little bit overkill, because you have the graph and you should be okay with making that determination from the graph. So now we have answered part A. The A value is the natural log of 3, because that is the point, the last point that it will pass the horizontal line test. Okay, so we have natural log of 3. Let's look at what part B is. For this value of A, find an expression for f inverse of x. Okay, so this is kind of a little bit of a tricky part. This one, it took me a second. I was like, well, because when you do the inverse, you switch your x and your y. And so we can say x equals e to the 2y minus 6e to the y plus 5. And you try to isolate your y. And you look at this, you say, well, crap, I can't take a natural log because there's 2 different e values. And my first thought was to factor it, but that still leaves your y values in 2 different spots. So then I thought, oh, we can actually complete the square. This is a quadratic in terms of e to the y. And you can complete the square on it. So x is going to be e to the y minus 3 squared. And why does that work? I'm not quite done, but why does that work? Because e to the y squared gives me e to the 2y. E to the y times negative 3 will give me this, because there's 2 copies of them. And then if I did negative 3 squared, I'd get 9. 9's too big, so I subtract 4. And now I'm back down to 5. So maybe you need to review completing the square. Not sure how fresh that is in your head. But now we have the y value isolated, so we can start solving for y. So we do things like add 4, take the square root, should be a plus or minus there. Then we're going to add 3, and then we'll take the natural log. And so I'll do those last two steps at the same time. We add 3 first, and then we do a natural log of 3 plus or minus square root of x plus 4, like that. So that's our inverse right there. So we can say that this is equal to y, or if we wanted to, we could call this f inverse of x. Now it also asks us to state the domain. And the domain of the inverse is the same as the range of the original function. And so the range of the original function is going to go from here on up. And so we want to find that value. From the graph, you could say it's negative 4. I mean, it looks like it's negative 4, but we should make sure. And so remember that we had found that our a value was the natural log of 3. So the f of a is e to the 2 natural log of 3 minus 6e to the natural log of 3 plus 5. So this gives me 9 minus 18 plus 5. Negative 9 plus 5 is indeed negative 4. So what's our domain? X is greater than or equal to negative 4. That's our domain. So I guess there's one other way you could have found that domain, which was by looking right in here at your inverse function formula, because you can't take the square root of a negative anyway. And so I guess there's 3 different ways to see that domain. The first way, from the graph, it looks like it's negative 4. Second way, from plugging in natural log of 3 that we found when we did part A. And the third way is looking at the formula for the inverse. So there you go. That's it on problem 9.